Hello to everybody who has joined us a little bit early this morning. We look forward to welcoming some others, so we'll just give them a couple of minutes before we start the meeting, but thanks for being with us today. So as we're at the top of the hour, I would like to wish everybody a good morning, good afternoon, and good evening. Thank you for joining us here today for the third in the Weidmann series of webinars today. We're talking about the much anticipated topic of accelerated aging test and the determination of Transformerboard thermal class. I have with me, there he is, Thomas Prevost, and I also have Brad Greaves with us from Weidmann today, both based in Vermont in the northeast of the US, who will be presenting today for us. As always in these Weidmann webinars, we would ask that if you have any questions, there are a lot of people joining the meeting today. So I would ask that you add your questions in the comment section. So if you look in the bottom right of your screen, you will see a button called questions. There you can privately submit questions, and we will certainly try and get to as many of them as we can at the end of the call. So I hope that we can answer all your questions. And as usual, you will receive an email after the event with a live on-demand download of the webinar. So if you want to revisit any of the sections, you can go back and view Tom and Brad again, or alternatively, if you know somebody that would be interested, you can also forward the link. It's available to everybody to view afterwards. So with that said, I would like to hand over to start with to Tom Prevost. I hope you all enjoy this webinar, and I look forward to seeing all your questions and being with you in around 45 minutes time. Thanks very much for joining us, and enjoy the session. Tom.
Thank you, Francis. Good day to everyone. It looks like we have a international audience, so morning, afternoon, evening. I think that'll cover it. So I will start this presentation with talking about a little bit of the history and the reason for the test that we did in trying to set the problem statement that Brad will then describe how we went about following standard test procedures to answer the question. So Brad's running the screen thing. So Brad, if you could go to the next slide, please. Okay, let's just start from a historical perspective and talk about the evolution of insulation thermal class. As we talk about that, the difference for cellulose-based insulation is the upcoming the initiation of thermal upgrading. So in the late 1950s, it was actually transformer manufacturers, not suppliers, that developed a chemical modification to paper, which has been now described as thermally upgraded kraft papers, with the abbreviation TUK, thermally upgraded kraft. By the early 60s, in fact, 1962, a standard organization in the US, NEMA, National Electrical Manufacturers Association, were the first standards to recognize the thermal advantage of thermally upgraded kraft in a transformer standard, in which they incorporated a temperature rise limit of 65 degrees C for oil immersed transformers. And I'll describe a little bit what this 65 degrees C average winding rise means. That was the beginning of an incorporation that was then adopted by the IEEE standards. And today, 65 degrees C rise transformers are the norm in North America, where most transformer specifiers use IEEE. The thermal upgrading is achieved by adding chemicals that protect the cellulose from oxidation. Thermal upgrading is primarily achieved using nitrous compounds such as dicyandiamide. So while thermally upgraded papers have been available since 1962, thermally upgraded pressboard, however, has not, which is kind of the foundation of what we're going to talk about today. So next slide, please, Brad. So with the ability to thermally upgrade paper, the transformer manufacturers were able to go from a 65 degrees C rise system to a 65 degrees C rise system. And the primary point is to look at what the hotspot temperature is. So with a 65 degrees C rise system, the temperature at the hottest spot in the winding is able to be 110 degrees C for normal life. Okay, next slide, please. So one of the things that Brad's going to describe, and it's kind of a question even within the discussion of when we're talking about thermal classes or thermal indexes. I took this from the IEEE test standard, which we'll talk about extensively later on. But this is a standard test procedure for thermal evaluation of insulation systems for liquid immersed transformers. And what the test program itself provides is the thermal index. So the thermal index is the maximum hottest spot temperature for which the insulation system is expected to provide normal life. If you remember the previous slide, the thermal index for 65 degrees C rise transformer, for example, is 110 degrees. So when we're looking at an aging test, the maximum hotspot temperature is determined by using the aging test and then rounding down to the nearest value given in this table, which I exerted from the standard. So if you look at thermal class here in table 2, a thermal class of 120 equals a thermal index of 110. So anything but if in the test, any result between 95 and 110, it would be then rounded down to the next value. So if, for example, the test came out with a thermal index of 115, it would be rounded down to 110, and then the thermal class is then 10 degrees C higher than the thermal index. I know it's a little bit confusing. The key point is that thermal class is 10 degrees higher than the thermal index. So we test for the thermal index, add 10 degrees, and that gives us the thermal class. And the basis of the thermal class is based on the fact that the thermal index is based on a 40-degree maximum ambient, where the thermal class is based on a 30-degree average ambient. Next slide, please. So when we look at our standards, the first thing I look at is the IEEE standard. So the general standard for transformers is C57-1200. It was last revised in 2021. And in this one section, which is the basis for the temperature limits, particular thing I want to look at is what I highlighted here is the fact that the requirement for the temperature limit applies to the insulation components that determine the minimum life expectancy. And this has been defined in the standards as the winding insulation or the conductor insulation, or if it's a layer type winding, the layer to layer insulation or the lead insulation, anything that's in contact with the conductors. So what has been interpreted by this standard is that the press board, which is not adjacent and contacting the conductor itself, does not need to be thermally upgraded. Next slide, please. If we switch over to the IEC standards, we can see a different concept of the value of thermal upgrading. So the last time that the main standard for that defines a thermal class for transformers was revised was in 2011. In fact, this is being revised as we speak right now, but the current standard states that there's only one value for temperature rise limits. And in fact, it says, if you look at this last statement, if not otherwise agreed between manufacturer and producer, the temperature rise limits given in Table 1 are valid for both craft and upgraded paper. And that's also discussed in 60076-7, which is known as the loading guide for over temperature. So in this case, the hotspot winding temperature, and these are rise limits, is 78 degrees because in the IEEE world, they assume a 20 degrees average ambient temperature. So in IEC, the limitation for the hotspot is 98 degrees. And again, so 98 degrees for IEC, and in IEEE, the limit is using thermally upgraded craft paper is 110 degrees, but the thermally upgraded paper or press board can be a lower temperature class. Next slide, please. I mentioned that the IEC transformer standard is being revised. That draft has been circulated the first time about 6 months ago. In fact, there were more than 1,000 comments on it, so it will take some time to be circulated and the comments addressed. In this new revision, we can see that in Table 2, there are now 2 thermal classes with the traditional 98 degrees hotspot, and then if you use thermally upgraded paper, now a new thermal class of 120 with a hotspot temperature of 110. And if we look at Note 3, it says that sufficient experience is available for transformers designed, tested, and operated according to the IEEE standard series with thermal class 120 using thermally upgraded craft paper to introduce this new thermal class. So 60 years later, after the IEEE has adopted 110 degree hotspot temperature using thermally upgraded paper, the IEC is now moving in that direction. Next slide, please. So to summarize, to look at the evolution, we went from non-thermally upgraded to thermally upgraded craft paper. That allowed us to go to a 65 degree C rise system. In the current IEEE standard, a 65 degree rise system is defined where thermally upgraded craft paper is required, but the thermally upgraded, or the board is not required to be thermally upgraded. The current, the upcoming IEC 7.6 Part 1 is introducing this same concept of a 65 degree C rise system using thermally upgraded paper. So if you look at the problem statement, and this, I'll let Brad take it from here, industry practice and international standards recognize the utilization of non-thermally upgraded press board with thermally upgraded paper as a 120 class system for mineral oil immersed transformers. And the question is, can we determine the thermal class of press board using an industry recognized test procedure? So how can we validate what the industry has recognized and is now being adopted into the standards? So with that, I'll let Brad answer this question. So Brad, take it from here.
Great, thank you, Tom, for that overview and history of thermal upgrading. So as Tom stated, now I'm going to look more into details of how we went about answering that. So first, when we look to determine how we can answer this question, we look to the IEEE C57.100 test standard. So this test standard provides guidance for such an evaluation with the so-called sealed tube accelerated aging test. And within this test, we first look at the industry proven system. Looking at table B1 within this test standard, we actually have two material ratios defined in this standard. First one being the power transformer materials ratio. And we can see in this table, this materials ratio has conductor insulation, which in our case is Weidmann thermally upgraded kraft paper. And we have high density press board, which again is Weidmann high density pre-compressed T4. We then look at the distribution materials ratio, where we see slightly different materials as well as being different ratios. So in this case, we have what's considered layer insulation, slightly thicker, same density, but still thermally upgraded kraft paper. And then we have low density press board, in our case, Weidmann high val, slightly lower density than our T4. Within both systems, we have some similarities. The first one being the same oil. In our case, a new degassed ASTM type 2 inhibited mineral oil. And then in both, we have copper and core steel. Looking back at the transformer standards that Tom mentioned previously, the C57-1200 brings this life equation or life expectancy curve shown on the right. The minimum life expectancy is defined in the standard as 20.5 years or 180,000 hours. And this again is the 65-degree average winding rise, 80-degree hot spot. So when we look at the minimum life expectancy curve and try to relate it to an accelerated aging test, we look at a maximum of 40 degrees C extrapolation from the thermal index, which again is 110, to the minimum aging temperature. Standard requires that we have aging temperatures to be 15 degrees apart. So using equation 1 from this standard, we can define our three aging temperatures at 150, 165, and 180, and a corresponding aging period to achieve the minimum life expectancy. So at 150 degrees, we have an aging period of 4,434 hours. At 165, it's 1,316, and 180 being 424 hours. And again, these are all points on this minimum life expectancy curve, which be equivalent to the 110 degree C thermal index and the 180,000 hours. So looking at some details of how this testing is done, we use a vessel, a stainless steel tube, approximately 100 millimeters in diameter, 210 millimeter tall. It's approximately 2-liter volume, slightly larger. It has a clamp-on lid shown here with a Viton gasket to ensure that we have a good seal on that lid. And it is fitted with a 10 psi pressure relief device. That pressure relief device is used first to keep a consistent pressure within that aging vessel, but also to ensure that we're not building up significant pressure where we have a potential safety concern within the test lab. With the material preparation, all solid materials, both press board and paper, are dried to a moisture content of less than 0.5%. And the liquid is dried using heat and vacuum to a moisture content to less than 4 parts per million. During the filling process of these vessels, after combining the solid and liquid components, the headspace is then flushed with dry nitrogen prior to being sealed, fitted with the cover and sealed. After the aging periods for each of these vessels, the solid material is removed, and then the machine direction tensile strength is tested on both the paper and the press board, as well as the degree of polymerization on both materials. So one of the first things to do when completing this standard or this test is to determine the end-of-life criteria of the system. So we do that by using the industry-proven system at the 3 time temperature combinations that I discussed on the previous slide, or 2 slides ago, along that minimum life expectancy curve. So the industry-proven system is aged, and then the tensile strength is tested following those aging periods, and that retained tensile strength is used as the end-of-life criteria for the candidate system. You can use other criteria such as DP or tear strength, etc., but typically it is tensile strength retention. When we look at our candidate system, that is prepared and aged in the same manner as the IPS until that end-of-life criteria is achieved. So again, we have 3 aging temperatures, 15 degrees C apart, the maximum 40 degrees extrapolation from the expected thermal index, and the minimum of 3 aging times per temperature. And what you're trying to do by aging the candidate system at multiple periods is to build these aging curves shown in this graph on the right. So under the same aging temperature, as we have multiple aging vessels, we see the degradation in the, in this case, tensile strength retention of our candidate system. So after the time, or after the end-of-life criteria is achieved, you interpolate on this line the actual time to reach the end-of-life criteria. So we have a line of best fit over the aging period, and the last, or at least one, aging period must be exceeding the end-of-life criteria, and then by interpolating that line, we can determine how long did it take to achieve that end of life. So following that, once we have the end of life, or the time to end of life for all 3 aging temperatures, we plot those points in a life expectancy curve by plotting 1 over the temperature in Kelvin versus the natural log of the time in hours to create a life equation similar to what we saw from the IEEE standard. And using that life equation, we can extrapolate the thermal index of that insulation system, and that's defined as the temperature at which 180,000 hours is achieved. So specifically for the testing that we had done, we had a test program with our standard material ratios, both power transformer with T4 and TUK, and our distribution transformer ratio with high val and TUK. We used the same 3 temperatures as the IPS, the 150, 165, and 180 degrees C, and we had multiple aging periods per temperature. We had slightly different for the ratios. For the power ratio, we actually had 8 in most cases, and for the distribution, we had 6. And you can see in the tables below the actual time periods that were aged for these systems. Anywhere at the highest temperature, a minimum of 1 week, but at the lowest temperature, you can see we went out to a maximum period of 62 weeks. Just kind of showing, although these are accelerated tests, they still do take a significant amount of time. And we defined in this test series our candidate system to be actually the transformer board within those material ratios. So now we'll look at a few observations that we made throughout these testing series. So the first one is the end-of-life criteria. So as I mentioned before, the end-of-life criteria is determined by the testing of the solid insulation, specifically the paper, following those 3 time temperature points. For the power materials ratio, we see a tensile strength of the paper, a retained tensile strength of the paper of 14.6% for those three time temperature combinations, and a degree of polymerization of 146. For the distribution materials ratio, we see quite a difference. We actually see retained tensile strength of 44.2% and a DP of 256. So after reviewing that and discussions, we believe that, the reasons for that is there is relatively more thermally upgraded paper in the distribution ratio, which is then slowing down the aging of all the solid insulation materials, including the transformer board. Additionally, there is relatively more solid insulation compared to the liquid in the power materials ratio, and this is resulting in more aging byproducts being generated and then further accelerating the aging. So between those two things, we believe that is why we see faster aging in the power materials ratio compared to distribution, resulting in the lower end-of-life criteria with both tensile strength and DP for the power ratio. Now, in order to try to confirm these hypotheses, another small aging test was completed. So for this test, we actually looked at the same material ratios, the power and distribution. However, we substituted thermally upgraded paper for non-thermally upgraded paper, really trying to see what the impact of the thermal upgrading agent had on the entire system. So we had power with the same T4, TU, and non-TU paper, and distribution in the same way. For this smaller test series, we did a reduced aging period of the 180 and the 165 for various temperatures, but really trying to build the same aging curves that we saw previously. So what we learned from this is we can look at the aging curves here. And if we look specifically at the high val and paper curves, so high val and TU paper is this blue curve here, and high val and the non-TU paper being this orange curve here, we see a significant difference in the aging rates and aging curves of those two ratios, with the only difference being the thermal upgrading, the presence of the thermal upgrading agent. We see a similar thing on the power transformer ratio side. However, there's much less difference here. The one with thermally upgraded paper is slightly higher than the other. And just to point out, I didn't mention before, but this is the tensile strength retention on the press board after these aging periods. So this is really the effect of the thermally upgraded paper on the press board aging in these two instances. So again, what we learned, kind of confirming what we had thought before, the presence of thermally upgraded paper in a relatively high proportion, as seen in the distribution ratio, has a strong influence on the transformer board aging. So this is indicating or leading us to believe that the same type of material may have different aging rates depending on the system of materials in which it's tested. We can see that from the aging curves here. The press board, the same press board, has different aging rates depending on the combination of materials it's aged with. And ultimately, this could lead to the same material having different thermal index when in different insulation systems. So now we'll look at a little bit of the results and the conclusions of the full aging test that we did. So the first thing to consider is the analysis method that was used in this project. So we actually looked at 3 different methods of analysis for this. Method 1, excuse me, is following the standard 2011 version of C57-100. As I described before, TUK is considered the industry-proven system. We looked at both tensile strength retention and DP at end of life. I previously mentioned what those end of life criteria were. And then in this case, we define the transformer board, both high and low density, as our candidate system. The second method that we used was looking back at a previous version of C57-100, the 1999 version, where we looked at the tensile strength retention of the individual materials. So here we had all materials, both the TUK and the transformer board, being evaluated with a criteria, end-of-life criteria of 50% tensile retention at 65,000 hours. So different from the first method, where we were comparing the transformer board to the industry-proven system, looking back at 180,000 hours. In this case, we looked at all materials independent of each other at 65,000 hours. And then method 3, similar to method 2, looking back at the 99 version, but in this case, looking at degree of polymerization. And again, all materials are evaluated independently of one another, but a criteria of a DP of 200 at 150,000 hours. So using those three methods of analysis, we end up with a variety of results described or summarized in this table here. So the first thing is looking at method 1. We're using, again, the 2011 version of this standard. We have the thermal index of the transformer board, both high and low density, being 120 degrees C. So as Tom described previously, using this method, we look at the thermal index being the point at which the minimum life expectancy curve crosses the 180,000 hours. For these materials, for the distribution ratio, that was calculated at 125, and for the power ratio, that was 129. However, as Tom described, this is then rounded down to the nearest 10 degree based on the table that he showed. So defining the thermal index of both of these systems or both of these materials at 120 degrees C. Using method 2, where we looked at each material independent of one another, we have, in this case, we're kind of comparing the thermal index of the transformer board to the paper. And in both cases, both distribution and power, we observed that the thermal index of the transformer board is slightly higher than the thermal index of the paper. The absolute thermal index of all of these materials for distribution ratio was, again, 120 degrees C, rounding down to the nearest 10. And for the power ratio, rounding down, was 110 degrees C. And we can kind of make sense of this being the distribution ratio, or the results from the distribution ratio being higher than power, based on the aging curves that we saw previously, in that the power ratio ages much faster than the distribution ratio. So when we look at a end-of-life criteria, the same end-of-life criteria for both ratios, in this case 50% tensile retention, we would expect that the power transformer materials ratio would achieve that end-of-life criteria quicker, in turn resulting in a lower thermal index than the distribution. Looking further onto method 3, this is using degree of polymerization with a a DP of 200 as your end-of-life criteria. We see with the distribution ratio, they're close. However, the board high val being slightly lower than the thermally upgraded paper in this case. In the power ratio, we do again see the board, the 2mm T4, having a slightly higher thermal index than the paper. And for all of these, we see a thermal index of 110 degrees C, rounding down, with the exception of the paper in the power materials ratio. So finally, I want to come back around to Tom's problem statement, and can we determine the thermal class of transformer board using an industry recognized test procedure? And the answer to that is yes. So for the first time in the industry, the thermal class of transformer board, both high and low density, was confirmed to be 120 degrees C through sealed tube accelerated aging testing. So following a industry recognized procedure, IEEE C57100, we established a temperature index of at least 110 degrees C, in many cases being 120. So with a thermal index of 110, as Tom described, adding 10 degrees to that to establish the thermal class of 120. However, in saying that, in that we were defining the thermal class of the transformer board specifically, we actually learned that thermal class definitions cannot be determined on an individual material. The thermal class is really on the entire insulation system. And in the instance of the industry proven system, that is thermally upgraded craft paper, the non-thermally upgraded transformer board, and mineral oil. Based on what we learned on the presence of the thermally upgraded craft paper and the impact of that on the aging characteristics of the non-thermally upgraded board, these systems must be tested and defined as the entire system and not the individual components. A few additional observations here is that the materials have a higher aging rate using the power ratio compared to the distribution. Two reasons for that is we believe the distribution has less solid insulation but more thermally upgraded paper in compared to the power ratio. And then finally, the presence of the thermally upgraded paper in the insulation system has an impact and reduces the aging rate of all the materials present, including the transformer board. And just to reiterate, as a result, these findings suggest that materials may have different thermal index values depending on the specific insulation system utilized, whether it's a specific liquid or the companion materials. Really looking at the fact that the entire system and all the components shall be tested, not individual components. So with that, I will hand it back over to Francis.
Thanks, Brad, and thanks, Tom, for the presentation. We have a lot of questions that's come in, so I am going to try and get to all of them. So we'll start off straight away. And just the first question to answer, because I know a lot of you asked, yes, we will distribute a copy of the slides after the presentation. So you can be rest assured you'll get those. So the first question I have is that we use the term high val, T4, transformer board, press board, all interchangeably at some point, I believe, in the presentation. So the question is, what's the difference or the definition in terms of what we've just presented? Tom, I'll leave that to you, perhaps.
Yeah, so I can take that one, Brad. If you have anything to add, then please speak up. First of all, I'm glad we have so many questions, and in my opinion, the question and answer part of these webinars is as interesting or even more interesting than the presentation itself. So thanks for all the questions. In regards to this one, it's really important to point out that the general industry term, so when I gave my presentation, I used the term pressboard. And that's because what the standards have defined for materials is based on either an IEC or an IEEE or ASTM material standard of the material itself, which is generically called pressboard. For the test that we did here that Brad described, we use specific Weidmann material. And I think Brad pointed that out when he was describing the way the test was set up. So these results are based on Weidmann transformer board. And when we use the word, transformer board is the Weidmann term for Weidmann pressboard. So that should quantify that. And then specifically for high density transformer board made by Weidmann, that brand name is T4. And for low density transformer board made by Weidmann, that is called high val. So when we look at these results, we can say for sure 100% that the thermal class of Weidmann transformer board is 120 degrees. We can't guarantee that for all other pressboard material. So I would say that that still has to be determined by the manufacturer of those materials or a third-party lab.
Okay, thanks, Tom. And just keeping this moving, one question related to the actual testing of the transformer board. Can you describe any challenges when preparing or testing the press board? So was there board delamination, warping of the transformer board material in the test that was seen?
Brad, I'll let you take that one.
Yeah, thank you, Frankie. So we did learn a lot in going through this process. Historically, these accelerated aging tests were focusing on the paper. So we didn't do a lot of attention onto the press board itself. In developing this test, moving to these larger vessels was a little bit of a challenge, determining the size that we really wanted, and how to prepare those in a different way. Still looking to achieve the same moisture content of less than 0.5% and of the materials, and then drying out the oil as well. And then in terms of testing, I think what we learned most is there is a difference in how the paper and the press board age in terms of aging rates. The press board aging a little faster in the early stages. So knowing that we needed to age or to test, have some early aging periods, specifically at the higher temperatures, to make sure that we caught that downward slope of the mechanical properties of the material. So there were some challenges in that way. Space in ovens was a challenge. These vessels are quite large compared to the old tubes, so that was something to work through as well.
Brad,
as far as the delamination, anything like that, one thing we do for all of these tests is all of the mechanical test samples are already prepared going into the aging vessels. So we had pre-cut the tensile strips, so they, after removal, we did not have to then cut them to size. The concern there is ensuring that we don't damage the samples after aging. If you remember, we had a very low tensile strength retention, specifically in the power ratio. These samples become a challenge to handle and must be handled with care so you don't actually damage them. So all of these samples are prepared in that way, so there's the least amount of handling necessary in order to get quality results.
Okay. Brad, how many ovens did we end up using for this series?
This one specifically, I think it was between 10 and 12. I don't recall exactly, but it was a significant number.
Yeah, so we have over 20 ovens in our aging laboratory set up because for every one of these temperatures and time combinations, we need a different oven. So quite equipment specific.
Okay, thanks for that. And I think you also touched there on another question we had about how did the transformer board compare with the TUK paper in the aging program. So I think we somewhat covered that. On to another question, a more specific standard-based question. So a question came in saying that they know the standards are centered around 50% tensile strength retention. Would there be a more appropriate end-of-life criteria for transformer board, and would we recommend that? I know we touched on this in the presentation. Is there any specific comment from Weidmann as a recommended end-of-life criteria for transformer board?
Maybe, Brad, I'll start, and then I'd love to hear your comment on this.
We have a lot of questions, Tom.
Yeah, so I'll go quick. So the latest version of the aging standard, the C57-100, has used not the definition of a specific criteria. So the latest version is that you test the industry proven system that you have as your reference point, and then you look at what that criteria is of whatever property that you're looking at the 180,000 hours defined end of life. And the challenge for that, and Brad brought it up also in his answer to the last question, with the power transformer material ratio, that value was 14%, if I remember exactly, 14.5%. That, in my opinion, is too low. The error that you get in the measurement is too low. So in the previous version of C57-100, we used 50% tensile retention. I like that value, but I also like the idea of using the industry-proven system. So I think tensile retention is the correct value, particularly if you're looking at other materials other than cellulose. A criteria like degree of polymerization you can't use with an aramid material, for example. So a mechanical strength retention, in my opinion, is the right one.
Okay, thanks, Tom. Brad, do you have anything to add to that, or can we move on?
I don't. No, I think Tom hit all the points that I was thinking of.
Okay, thank you. We had a question about the difference in the DP and tensile strength with power transformer and distribution transformer material ratios. They would like a more technical and physics-based explanation and to understand that a bit better. I don't know whether that's something we can answer quickly, Brad, or whether that's something the particular individual can contact you directly about for more information.
I think for me, I'd like to know more specifically what they're looking for. Quick answer for that. I think with the press board, transformer board, you see more, because of the thicker samples, you see more fiber entanglement and more bonds between layers, which would impact tensile mechanical tests, but may not impact DP. So you see some differences there. But I think if that individual wants to reach out and ask the question specifically, I can answer it.
Okay, thank you.
Just to add to that, just traditionally, even if you look at the old C57-100 standard, if you use the DP of 200, the end-of-life criteria was 150,000 hours, and if you use the 50% tensile retention, it was 65,000 hours. So even back then, they recognized that it's two different measurements. You're not going to get the same with 200 DP and 50% tensile retention.
Okay, thank you. Question regarding type of transformer. Given that the material ratios affect the result of the aging test, there's an implication that the equipment will have different behavior in operation. The question is, does that mean that there will be a different behavior in a core type and shell type power transformer?
So I think if I'll start, Tom, I think the first thing to note here is by using the most recent standard testing standard. And so although you get different end-of-life criteria, we actually did get similar thermal index values of the two ratios. So by combining or by comparing to the industry-proven systems, I think you can negate that a little bit. And then shell types, there's no mention of shell in the IEEE version. I believe in the IEC version of aging testing, there is even a different ratio for shell type transformers.
Okay, thank you. I have a couple of quick questions for you. I would prefer one-word answers, please, if possible. So this one to Brad: was the end of life determined using paper or transformer board?
The end of life for the industry proven system was determined with the paper.
Okay, thank you. Tom, does Weidmann have any plans of determining thermal class of cellulose-based press board in fluids other than mineral oil?
Yes, in future, yes. Yep.
Okay, thank you. And does this also apply for laminated press board, so K-zine or polyester glued?
Yes.
And Brad, have we evaluated?
I say yes, but not that hasn't been validated.
Yeah.
And the interesting part of that for laminated press board would be, what would you use for end of life criteria? Because it's used for typically in compression or in flexure, so it would be much more challenging, I should say.
Okay, thank you. Brad, have we evaluated the test results as per the latest IEEE C57 100-2022? Is it even possible to do it with this test setup to that standard?
So unfortunately, we can't use the raw data with this test series and evaluate it using the new test method, specifically because, or mainly because, it's a new ratio has been defined. New materials ratio has been defined in the latest version of C57-100. Although the actual calculations, the end of life determination is the same, the calculation process is the same, but mainly with the ratios being different, we're unable to do that.
Okay.
Just to add real quick, I know you want a one-word answer. The latest version of the C57-100 standard, actually based on a review of this paper that was written, this was written and published in IEEE Transactions, but there's only one there's no, in the current version of the standard, there's not a distribution and power ratio. There's only one ratio, and that has been changed to a different ratio. To Brad's point, that ratio, because what we learned here, has a tremendous influence on the results. So you would have to repeat the test. But we're very confident that the 120 class would still be verified.
Okay, thanks. Tom, what is the relatively high proportion of TU paper in a kraft and thermally upgraded paper system? So what is a relatively high proportion of thermally upgraded paper in a kraft paper system?
I can say that in general. I don't have the number, the ratio in front of me, but what we see is, when we look at the table B1 that I mentioned before, is in the distribution ratio, you see a very high amount of paper and very low amount of press board. So in that, comparing the board to paper ratio is very high compared to the power ratio, where it's closer. There's less paper and more press board in that case. So I believe that statement was based on, in the distribution ratio, there's so much paper compared to relatively low amount of board, the impact of the influence of that paper was much greater.
Okay, thanks. Question about in application and relating to moisture. do we have any idea, or have we studied the effect of what 2% moisture in paper how that would impact the results?
Stay tuned. That's the next series of testing that we're doing. Obviously, moisture has a tremendous impact on the rate of aging. That's been well studied, but we are doing more testing to understand it specifically in these accelerated aging tests, and then what our plan is to be able to translate that into what the impact on full-scale transformers. But that's more research that is currently ongoing.
Yeah. Question related to our partnership with DuPont here. Do we have any idea how transformer board thermal rating is affected when Nomex is used on the wire or on the wire and key spaces?
No.
Yeah, no.
Okay, to be continued there. All right. An interesting one here, and I'm not sure if it's more insulation system that we're focused on or T4 itself, but someone has asked the question, does this mean that T4 is qualified to be a thermally upgraded board? And if so, does that apply also to other transformer board products from Weidmann, such as TX2?
No, I don't think that this can translate as thermal upgrading. I mean, if I'm looking at thermally upgraded paper, I know that I was able to attain that higher thermal class because I added a nitrogen-based compound, and I can verify that it's upgraded by measuring the amount of nitrogen in the paper. This transformer board, again, it's Weidmann transformer board, is based on the way that the board is manufactured, what the cleanliness of the raw materials are. If we were able to chemically modify it, then it would then be you could consider it a thermally upgraded board, and likely it would have an even higher thermal class. The challenge, I mean, I anticipated a question of saying, why don't we just thermally upgrade board? The challenge is that these chemicals are, they're not environmentally friendly. If you remember, I called it dicyandiamide. The cyan is like cyanide. So in paper, you can keep that in a very controlled volume. If you were trying to thermal upgrade press board, it would be not a very environmentally friendly process, and also very costly. So I think that you could thermally upgrade a board, but what we've seen from this test is you don't need to. The board not thermally upgraded has the same thermal class as thermally upgraded paper when they're used together.
Okay, good. We only have a couple of minutes left, so I want to try and get through a couple of more questions. Just a quick one from a friend of ours. Did you test both high-val and T4 in the power system, and was there a difference?
Well, we did at one point. I didn't review it here, and I'm trying to remember. I don't believe there was a significant difference between the aging results of the two. But
yeah, it wasn't, because we wanted to understand, what was affecting what. So we did test with the same ratio, the high and low density board, and it was more a result of the ratio than it was of the board itself.
Okay. Just on a gas generation question here for you. If we consider now T4 as having the hotspot rise limit of 80 degrees C versus 65, what would be the CO and CO2 generation compared with the existing rule? Do you have an answer for that off the top of your head, or an idea?
Well, I can answer the top of my head is that if you look at IEEE standards, they have, I believe, around the same gas generation criteria during the factory acceptance tests as the IEC standards. And the industry practice is to use thermally upgraded craft conductor insulation and non-thermally upgraded board and very, very, very often they're able to meet the gassing requirement. So based on that, I would say that there should be no difference.
I'm only going to get 2 more questions in, unfortunately, but did we measure nitrogen content in Transformerboard after the aging test along the same lines?
We did, right, Brad?
I believe, I'm thinking back, and I believe we did, but I don't, off the top of my head, recall the results.
All right. Well, my recollection is, because that was one of the theories, right?
Yeah.
That some of the thermal upgrading agent is actually transferring via the oil into the board. We did not measure appreciable amounts of nitrogen in the board. So that's a great question, and we did test that theory, and it wasn't in fact nitrogen or TUK chemicals, this dicyandiamide, moving into the board. I assume that's why the questioner asked that question.
Okay. Well, with that said, unfortunately, we have lots more questions, but we can't get to them right now because we're up to the hour. So I would suggest, I'm sure many of you have Tom or potentially Brad's contact details. I encourage you to reach out to them. As Tom said, he loves a good Q&A and somebody to challenge him with a strong question. So feel free to reach out to them directly. If you don't have their contact details, I know, I believe my address has been coming to you all as part of the reminders and so on. So feel free to reach out to me and I will connect you with Tom or Brad. So finally, thank you to Tom and Brad for the presentation today. And thank you to all of you for joining. I know we've been pushed with time and we're a little bit over, but I really appreciate you all hanging on there until the end of the session. And apologies if we didn't get to your question, but I promise Tom and Brad will be more than happy to support you with answering those questions as we go forward. Again, we will distribute most likely early next week an on-demand recording of the session. So if you missed any of it, I know some of you said you were a little bit late getting in, then we will certainly provide you a full copy of the webinar, and I will make sure you all get a copy of the slides for your reference as well. So thank you very much. We look forward to seeing you in the new year with another Weidmann webinar. Feel free to contact us if you have any ideas for a session. And we'll try and fit that in. Enjoy the holiday season if you are celebrating, and we look forward to seeing you in the new year. Thanks very much. See you soon. Bye-bye.
Thank you.